Hello and welcome to this video lecture on heat integration, pinch technology, minimum number of utilities, minimum number of heat exchangers method, part 2, stream identification. Reviewing the 6 steps in heat integration, step 0 is to make sure our process is optimized. We've chosen a minimum approach temperature of 10 degrees centigrade. The next step is to determine which streams need to be heated or cooled. Write down their flow rate times heat capacity, their inlet and outlet temperatures, as well as their heat. So we're going to review our definitions. A hot stream is a stream which has heat to give. It starts off hot. A cold stream is a stream which needs to be heated. This means that when we calculate Q, which is heat, a positive Q means that the stream has heat to give. In other words, a positive Q is associated with a hot stream. A negative Q is associated with a cold stream. It means the stream needs heat. So positive Q corresponds to a hot stream, negative Q corresponds to a cold stream. We're going to label all the streams coming in and leaving any heat exchangers or furnaces in our flow sheet. So let's bring up a flow sheet here. Again, this is based on the example from the Turton textbook. And this is in the pinch technology chapter. And I've just written down the temperatures for various streams in this flow sheet. We have to label these streams based on whether they need to be heated or cooled. So let's first identify which ones are hot and cold streams. Starting from the left here, we have 2 cold streams, probably different flow rates, both being heated up to 190 degrees. They are combined in a mixer, sent through a compressor, and then heated up to 290 degrees. This is a cold stream. After the reactor, we have a hot stream being cooled to 150 degrees, and then 2 hot streams coming out of the distillation column after this reactor. The next step is to consolidate multiple adjacent streams and number them. So I have labeled all of these streams in blue if they are cold streams and in red if they are hot streams. And it's important when you're consolidating multiple adjacent streams and numbering them that you don't include turbines, compressors, reactors, distillation columns, condensers, reboilers. The only thing you are including are heat exchangers and furnaces. So we can label or number these streams however we'd like. I'm going to follow the convention in the Turton textbook, and they number hot streams first. So you can number these streams 1, 2, 3, or you can number them 3, 2, 1 or 2, 1, 3. The numbering does not really matter as long as they're numbered. The cold streams are numbered 4, 5, 6. Again, you can number these from left to right, right to left. It doesn't really matter as long as you designate a number for these streams. Notice that streams 4 and 3 that have multiple heat exchangers have been consolidated. The next step is to determine the inlet and outlet temperature for each stream. So I'm going to label the hot streams with their inlet and outlet temperatures. Again, notice that stream 3 has a consolidated temperature out. So the T in is 200, the T out is 500, not 100. Similarly for streams 4, 5, 6, I'm labeling here the T in and T out. For stream 4, I've consolidated these temperatures. T in is 190 and T out is 290. The next step is in a table to write down the flow rate times heat capacity, the inlet and outlet temperatures, and the overall Q. So I've created a table here. There's a lot of information here, but the information in red is for hot streams and the information for the cold streams are in blue. So I've labeled the streams as hot or cold. I've put their flow rates and heat capacities in the table. This information is provided by Aspen. And you may be wondering if you have a stream that is undergoing a phase change, the heat capacity is changing. It's not constant. So if you need to take an average of the inlet and outlet heat capacities for your stream. And again, it's the overall in and overall out that you're averaging. After that, you calculate the flow rate times heat capacity. Then you put the inlet and outlet temperature. And then you can calculate the overall Q for each stream. This is the flow rate times the heat capacity times T in minus T out. And I have this in units of kilowatts. Something to keep in mind is that there is an overall heat deficit for this process of minus 50 kilowatts. So we need to find 50 kilowatts of heat from somewhere in order to balance this process in terms of heat.